which was actually an off-the-shelf aircraft.
So we didn't. That one looks kind of janky. We didn't build that one.
We didn't build that one, but we stuffed our own electronics into it and learned a whole lot. And then ended up building this next prototype here, which we call Goose.
Okay.
And then iterated a few more times. There's actually a Cardinal generation aircraft that we don't have on the wall. And then Quail, which is this second from the bottom aircraft right here. There's actually another one up top. So
that one looks a little more beat up than the one on the wall.
Exactly. So this one on the wall has actually never flown. That was a show plane. Whereas the one up on the wall, Quail 30, that one came back from Rwanda after 2 years and over 10,000 deliveries made.
Okay, so 10,000 just from that one aircraft.
That one aircraft alone, exactly.
Wow, that is incredible. And then this is the newer version.
Yeah, so, well, this is the previous version.
Previous version.
This is then Robin.
Okay.
Which you can see kind of with each aircraft, they get a little bit more sophisticated and a little bit more streamlined.
Yeah.
So Robin,
I noticed there's like one propeller on the first one, and then it switches to 2 propellers. It looks like there's a lot more complexity, like you mentioned.
Yeah, and a lot of sophistication. You know, with each, we learned a whole lot. We learned about what worked well. We learned about how do we actually harden these aircraft to work in the real world. And so, you know, we went from 1 propeller to 2. Then the problem with the 2 propellers on the wing is if you lose one, they're off center, and so you kind of have this twisting motion.
I said we're live. Anything can happen.
Yeah, we've got a busy facility here, as you're seeing. But yeah, you know, Goose up there was also the first generation of Zip that had a parachute built in. So you can kind of see that black hatch over the top of it. And, you know, we realized having a parachute on board would really help when we were flight testing the system.
Yeah.
You know, if things go wrong during a test, we can have a parachute pop and we can float down
So
gracefully.
it's just part of safety.
Exactly. And
All the redundancy, all the parachutes.
Exactly. You know, again, we operate 24/7, 365, rain or shine, through thunderstorms and snow and sunny days, and really, you know, try to design the system to withstand all the different elements.
And that's important because something we sometimes hear about drones is that they can't fly in all conditions, but really starting in Rwanda, starting with a medical use case, we had to be able to fly
Exactly.
in pretty much anything.
Yeah, you know, when people were counting on us to deliver, we very quickly learned that not being able to fly because of the weather wasn't going to be acceptable. And actually in Rwanda, you know, we're flying in the second most lightning struck place on the planet. So there are a lot of thunderstorms. Those storms pop up out of nowhere. They race across the horizon really quickly. And, you know, we launch in sunny conditions with no wind, send the Zip over the horizon. And, you know, it was pretty early on in our operations back in 2016 that Zip would come back soaking wet. So it experiences all sorts of things when it's, you know, again, flying over the horizon, over mountain ranges, windstorms, you name it.
It's not just a parachute and extra things, but there's extra waterproofing, there's extra capabilities. The flight computers are getting much more sophisticated. I think we're going to actually see the latest one pretty soon.
Let's go get hands-on with some Zips close up. But before we go there, we also have this live counter. So we've done 1.3 million deliveries to date. This counter is ticking up by about 1 every 60 seconds now. And that tornado of Zips flying around the number is actually a real-time count for how many Zips are in the sky worldwide right now. So we can see a whole bunch of Platform 1 Zips flying in the many countries we're flying in. And then also, if you look closely, every so often you can see a Platform 2 Zip, like here on the bottom going by. Yeah. So that's a Zip flying at our test site.
I mean, so there's like a couple dozen in the air right now that's real time as we are speaking. We're making deliveries continuously.
Exactly. And, you know, for most of our operations, this is actually the off hours because, you know, it's late at night in Africa. Whereas, you know, 8 a.m. Pacific time, when I come in the morning, you can almost not even read that number. There's like such a cyclone of Zips flying around.
Yeah, it starts to obscure it because it's so dense. And I know long-term our ambition is for that thing to be even more filled.
Yeah.
Well, let's check it out. So these are not Zips.
Yeah, so down here, so this whole floor used to be our manufacturing lines. And actually over the last 6 months, we've kind of outgrown the space. So every Platform 1 Zip that's been sent to production was built down here.
Yeah.
And until earlier this year, Platform 2 was also being manufactured down here. But as you can see, if you peek over the curtain, really, you know, as the engineering team expands, we take every nook and cranny of the office. And so we actually graduated manufacturing to a much bigger facility about a mile up the road. But we do still have a few demonstration zips that we can get our hands on.
Okay, so this is the latest P1 zip model. This is Sparrow.
Exactly. This is a Sparrow 2.0. So this is actually our 9th generation aircraft.
Wow.
You know, many cool refinements and improvements through each generation to get to a system that lasts, well, a whole lot. a whole lot of deliveries. So.
I already see, you know, I care a lot about redundancy, and I can see, I don't know anything about electronics, but it looks like there's 2 of everything.
There's a lot of symmetry in the aircraft, right? We've got the 2 motors, and then if you look at the tail, the control surfaces on the tail are split, so we've got 4 rudder vaders.
And so that's if one fails, the other one will still work.
Exactly. We have 2 GPS receivers, 2 flight computers, 2 of pretty much everything, because if any wire becomes unplugged, any part glitches out, anything, you know, any subcomponent fails, the whole aircraft can continue to fly just fine.
That's super cool.
Yeah, and so this aircraft is very modular by design, right? Mm-hmm. If a given component fails, we can easily swap it in the field. And between each flight, this zip comes apart into 3 pieces. So we have the main body of the aircraft here. We have the wing. This is actually half of a wing. The full wing would go up to almost the height of the ceiling.
Yeah, it's like, what, 11
very
feet?
Long. Yeah, it's a very long and highly efficient wing. And then we have the battery right here that we swap between flights. Mm-hmm. The construction of the aircraft is also really impressive. Yeah. So every single gram we can shave from the aircraft is an extra gram we can carry as payload. And we can carry that gram an extra, you know, kilometer.
And that's just because, you know, weight, right?
Weight is
like
really
we have to carry
aircraft.
things,
Yeah,
and
exactly.
so if it was too heavy, we wouldn't be able to fly.
Yeah, and so this is the core skeleton of a Platform 1 zip. So basically, this skeleton here then has these foam panels mounted onto it as aerodynamic surfaces. They're very lightweight, but they're not structural.
Mm-hmm. This is like a helmet.
Like almost. A bike helmet, exactly. These just kind of like pop on, but the entire structure is this composite carbon fiber sandwich. So here, I'll let you...
Oh, I don't need 2 hands for this. I can take this with my pinky.
Yeah, exactly.
That's
it's
so
very,
light.
very lightweight.
So is this like foam as well, like high density foam in the middle there, and then this is carbon fiber?
Exactly, yeah. Really easy construction technique.
And this is where the box would fit.
Exactly. So the zip would fly like this. This entire cavity in the belly is the size of the payload.
That's awesome. That's really cool.
And then this tiny little hook here, this is our landing gear. So that's how we land. Again, every single gram we can remove from the aircraft is a gram of payload we can carry. And so if this, I think this weighs like 11 or 12 grams, this component, that's all we need to land.
Because this is what catches it. This is the. I know we have a whole catch, you know, recovery system.
We'll have to get into that another time. Yeah.
Yeah.
Whereas in comparison,
and all of this system, what you're telling me though, is really designed for long range, right? We needed to serve people a long way away from a center. Can you talk about how that informed?
So the biggest design requirement for Platform 1 is for a big remote region that has, you know, challenging terrain, challenging weather, maybe poor infrastructure or remote communities. It really makes sense to centralize all the inventory in one location. And at that central warehouse, we build a launch facility where we launch and recover the aircraft. Yeah. And then every extra kilometer we can fly is that much bigger of a region we can serve from that one distribution center. And so this system is really, you know, for example, we cover the entire country of Rwanda with 2 distribution centers, one in the eastern half and one in the western half. And so, you know, again, really designing we fly quite fast, we fly through all elements, and we deliver on demand. So these remote facilities don't need to keep any inventory on hand, but instead, when an order comes in, we're able to quickly pack that into the belly of the zip, slap a wing on, slap a battery on, launch it, and the zip flies out autonomously, delivers without any infrastructure on the ground, right? It just opens the belly doors, drops the package out, turns around and flies back.
And it kind of floats down with a parachute.
Exactly. Yeah. One other thing I want you to take a look at is the Platform 1 battery. So here, you can go ahead and grab it by the handles.
All right. Yeah, so that's a little heavier than the. This is heavier than the rest of the aircraft.
That's nearly
it feels like.
that's nearly half the weight of the entire aircraft.
Wow. This is what gives us the ability to travel so far.
Exactly.
That's awesome.
Yeah. Now let's take a look at Platform 2. So we have a Platform 2 Zip here.
This is the new model.
This is the new model. So Platform 2, at a high level, similar size to Platform 1, kind of looks quite similar. There's a few extra bits going on with Platform 2. Mm-hmm. Really, when we got Platform 1 to the point where it was working well, we asked ourselves, what problems do we want to solve next as a company? And Platform 1 works really well in more remote regions, but in denser locations, really, there's a pretty different set of product requirements you're trying to optimize for. Range doesn't matter so far, or as much. But the thing you really want to be able to do is, one, we want to be able to pick up inventory from locations that already exist. We don't want to have to centralize things, right? Here in South San Francisco,
we already have Walmarts. We already have these places.
Yeah. How many pharmacies are there within 5 miles of us right now? Probably dozens, right? We don't need to build another pharmacy. So we want to be able to quickly integrate and pick up from an existing facility. So we'll show you what that looks like in a minute. And then we want to be able to deliver to a much tighter area. So for example, a doorstep, or if you've got a really small side walkway between your house and your neighbor's house, or you've got a small back patio with a little table on it, how can we deliver precisely to that location while keeping the aircraft as far out of sight and out of earshot as possible to build an invisible layer of infrastructure?
I would say I grew up in rural North Carolina, and we had a backyard that I think was probably big enough and rural enough to be served by P1, but now it seems like I live in an apartment building now in a city, and this would be able to get a delivery to me.
Yeah, totally. So Platform 2 has a bunch more motors. So we've got these 4 hover motors that allow the
so
Zip
there's
to
a motor
stay
on
still.
each.
Exactly. Each of these is a motor. But again, kind of high level, it's a composite airframe. It's ultra lightweight, one big component. And if we pop the hood real quickly, you can see it's similarly foam panels with a whole lot of smarts under the hood.
I say it's similar to the first one. I see redundancy. I don't know what any of these things are, but I know there's 2 of all of them.
You nailed it. So exactly. And then similar to Platform 1, the belly is a big open cavity.
Okay.
So if you want to take a look under the hood, you can see there's quite a bit of space in there.
So really, there's a lot. It seems like we learned so much. You said 9 generations
of Platform 1.
And we've taken all of those lessons and kind of made this new thing, taking that into account.
Exactly. So, everything we've learned from, over 1 million deliveries, I think we're closing in on 100 million kilometers flown.
Yeah, we're at I think 93 million miles. So
well past 100 million.
Well over 100 million kilometers.
And we took all of those learnings and have spent the last few years designing, building, and testing Platform 2. But the hover motors allow the Zip to stay still, but it still doesn't explain how do we get down to the ground to pick something up, and then how do we precisely put a package down. And so in the belly of the Zip, we have the droid, which is this little robot. This is actually an earlier prototype, so this entire thing is 3D printed. So let's actually go take a look at our setup over here.
Yeah, I can't wait to see it. So it's lunchtime.
Yeah, exactly. So right behind our cafeteria line, we have what we call a wall portal. So we have a few different ways in which we can integrate with our partners to go and pick up products. But if you could imagine a window being modified to become a magical portal, we call this a wall portal. Outside, we would install a dock, and the Zip lands in the dock. Out of the belly, on a string, we lower down the droid.
Can we see kind of what this looks like?
And all you've got to do is open the window, and a droid appears.
So this is a droid. It looks.
I call it like the most futuristic toaster you could imagine.
I was thinking, cool. It's like thermally insulated. It's all this stuff.
Yeah, and so you can open the lid. All it takes is you open the lid. We've got a few boxes we can load into it right behind you.
Yeah. So how much does this fit?
Quite a bit. I mean, you can see here. So What is each of these? Would these each be 6 donuts?
6 donuts.
Okay, so you could fit 18 donuts, for example.
And you just put it
with
in.
room to spare. Just put it in. You just close the lid. You would scan the order receipt, and that would tell the system this droid has to go to this person's home to deliver it. The zip outside would retract the droid automatically, and the droid would get whisked away.
So what I'm noticing about this is, if I'm a business, if I'm a restaurant, I need my team to be really efficient, and sometimes if you have to like run outside or you're doing a lot of orders, this seems like a really easy way to fulfill orders really quickly. You don't even have to go outside.
Yeah, exactly. And this system here at our HQ isn't operational because we are sitting right next to SFO, so we can't actually fly here. Maybe someday. But this is a wall portal. We also have other setups that are much easier to install.
Yeah.
For example, if a business wants to get started much faster, we can drop down what we call a kiosk in the parking lot, and they can load a droid outside in a stand, essentially.
Great. So there's a lot of flexibility. It sounds like depending on what you need, what you're looking for, someone on the team has thought about it and come up with a solution.
Exactly. And then the cool thing about the droid, so this explains how we can pick up products.
Yeah.
But we also mentioned that Platform 2 is all about precise delivery while providing a silent, invisible delivery experience.
Okay.
So this droid would live in the belly of the zip way up high. The zip is 400 feet up. And when it arrives at your home, the droid descends down. The zip stays high.
Okay. So the big aircraft we saw, that stays way up high.
That's a speck in the sky.
It's
you
a
wouldn't
speck in
even
the
notice
sky.
it's there.
And that's, I would assume it's for noise, it's for safety purposes.
Yeah.
No one has to actually get that close to it.
Exactly. It's never coming near people.
And this thing, it just looks kind of cute.
Yeah, exactly. This is, like a cute little Pixar character. People love the droid. It's really cute when it's flying around. It's basically got this big, slow-moving pusher prop in the back to fight the wind.
Yeah.
And then it's got these cute little thrusters that make this squeaking sound. That's how we named it the droid. It sounds like it's making beep, boop, beep, beep, bop
That's
sounds.
cool.
And that allows it to steer, point into the wind, and fight the wind. And then on the bottom, you can see it's got a handful of different sensors to be able to figure out where to deliver to. So, for example,
Amazing.
it would see, hey, there's a clear flat table here in
Yeah.
your yard.
It comes down.
Come down.
The doors
it's got
open.
doors on the bottom. Exactly. Yeah. And, I like to describe it as, the classic magic trick where the magician takes their hat off, they put it on the table, they lift it up, and there's a rabbit.
Yeah.
Exact same thing happens with the droid. The droid touches down and immediately lifts up, and whatever you ordered is left behind.
Amazing.
We don't need any special packaging.
Very cool. So in a delivery itself, it just takes a few seconds. It seems like it comes down.
Exactly.
It makes it finds the safe place to make a delivery, and then it opens the doors, and then it goes back up, and in and out super quickly.
Yeah.
Awesome. So I know we have another location, I think.
Yeah. Let's go upstairs.
And so one thing I'm noticing, we're building a lot here. We've talked about several different subsystems, several different mechanisms. So all of that is made in-house.
Yeah, exactly. So Zipline is a very vertically integrated company, and that basically means we're not buying drones off the shelf.
Yeah.
We're not selling the drones either. We design every single part of the system.
Yeah.
We build them ourselves, we test them ourselves, and then we operate the entire system ourselves.
So why are we doing that?
Yeah, it's a lot of work.
Because I've got a cousin with a drone. He bought it from Amazon. It was worked out.
Yeah, it ultimately comes down to a handful of things. Easier said than done, but we care a lot about the safety of the system. So we have a lot of redundancy. When you're buying a drone off the shelf, that system can fail in a whole bunch of different ways. It's not going to survive all the different elements, and it's not going to last for hundreds, let alone thousands, let alone tens of thousands of flights. When there are problems found with it, if we bought something off the shelf, we don't have the flexibility to solve those problems ourselves, unless we own all the complexity and we have the experts in the house.
And it looks like we have some experts in the house.
Yeah, exactly. So what you're seeing up here, so this is the engineering team. And so over here we've got the autonomy and perception teams. We have the system validation team, the embedded software team. Back against the wall we have the firmware team. And then if we keep coming this way, we have flight controls. We have the weather team. You can start to see how basically each component of the aircraft has a team for it. In this room, we've got hardware teams. So we have powertrain. We have the systems engineering team sits over here.
One thing I've heard before is that if we part of the hard element of being a drone delivery company is everything has to be good. If there's one area that's weak, it doesn't work. If we have the best hardware in the world, but the software isn't up to par, it won't work. But
gravity doesn't give
everything has to be on 100% of the time. It sounds like as we saw, we've got dozens of aircraft in the air right now using our software, using our hardware. That's so cool.
Yeah, exactly. And so, we do a whole lot of development here, right? We've got hundreds of engineers working to make the system better, cheaper, more reliable every single day. And showing that all of those changes are working well is also a really important thing, which brings me to the last stop on our tour and easily my favorite room in the whole building.
I say we're deep in the corner now.
Yeah. So come on in, I'll show you around. This is our Hardware in the Loop lab.
Hardware in the Loop.
Yeah, exactly. So you're essentially stepping into the Matrix right now.
It feels like it.
Yeah, it's very sci-fi in here. So there's a whole lot to talk about here. You can take a look around. Basically what we're seeing is every one of these shelves is a full Platform 2 system flying in the Matrix. I think that probably...
Flying in the Matrix.
That probably creates more questions than it answers.
I was going to say, I see some rabbits. Walk me through what that means.
Yeah, here, let's start by talking about this system here. I'll break it down. So this here is all of the electronics in the Zip.
Okay.
The main aircraft that's flying.
These are production aircraft hardware.
Exactly. So this is we have the power distribution board, we have the flight computers.
I see the motors.
We've got all of the motors. We have the 4 hover motors, the 1 mixed motor. We have all the antennas that we use for communication, GPS, Wi-Fi. We also then have the droid, its sensor payload, and all of its electronics.
So this is a table of the brains, pretty much.
And the dock as well that the Zip goes and lands in. All of these electronics with a whole lot of wires. You can get a look under there.
This is complex.
They're all strung together and plugged into this test computer here. And basically, this aircraft has no idea that it's sitting on the bench here in our lab in South San Francisco, but instead, this computer is running a simulation. This is why I call it the Matrix. This aircraft thinks it's out in the world flying somewhere right now.
That's the Matrix.
That's the Matrix.
It thinks it's flying a real... And so are we like simulating the physics? Like how detailed is that simulation?
Yeah, so we're doing a full high-fidelity physics simulation. We're simulating weather. We're simulating the physics of flight. We're simulating faults. So all the electronics are also plugged into these digital relays where we can basically programmatically break any one wire in the system. Remember downstairs we were talking about all that redundancy where we've got 2 GPS antennas, for example? This system here can go and unplug one of the GPS antennas midway through flight to make sure that we both detect that fault and we continue to fly despite losing one sensor.
So is one way to think about this, aircraft are valuable, we want them to be super safe, and so we're making sure we're testing out everything that could possibly go wrong in simulation before we do it in the real world.
100%. So in this room we've got dozens of hardware in the loop setups.
I said there's a lot of them.
Yeah, these are all hooked up and they're fully automated. And basically what's happening in here are a few different things. One, we just saw all those engineers working on making the system better. Anytime an engineer is proposing a change to the system, we automatically run it through a barrage of tests to make sure that change in and of itself simply makes the system work better. And then 2, when we have a whole batch of changes that we're gearing up to release to the world, we run thousands of simulated flights across all sorts of conditions. We test different weather, we test different mission types in different geographies, different fault conditions in flight to make sure that all the critical safety systems continue to work before we then graduate to flight tests.
So Joe from LinkedIn came in with a question asking about icing, de-icing, these weather situations. So we're simulating weather in simulation here, and then I know we're also flying real world weather tests kind of around different parts. I think we have a test site in Wyoming.
Correct.
Can you talk at all about how that's going, what we're seeing?
Yeah, so we like to consider all of our test systems as layers of Swiss cheese, where any one test system is going to have some holes in it, where it's just not going to be able to, for example, these computers aren't actually getting very cold, right? We might tell them they're cold, but they're not actually being subjected to different weather elements.
It's a temperate room.
So this system can test how the software handles, and if, for example, we tell the system it's too cold, the software should say, don't take off, we're too cold. We can test that. But what actually happens at a physical level if we're flying in flight and we start to accumulate ice, we need to actually go out into the real world and test that. And so that's where, Zipline HQ is just one of many facilities we have. We've got test sites all across the US, testing in different environmental conditions. We've got ones in coastal California that get crazy windy salt fog. We have ones in the Central Valley where we get crazy high heat. It regularly breaks 120 degrees Fahrenheit in the summers.
Yeah.
And then when California doesn't get quite cold enough, we test in places like Wyoming, where we test, up to negative 30 degrees Celsius.
That's amazing. And I heard one of our colleagues was telling me the other day about how some of our team members have to get up actually like in the middle of the night, super early when it's coldest, because it's not just enough to be in cold Wyoming weather in the winter. It's like, okay, what's the absolute coldest time of the day? It's 2 a.m., 3 a.m., and they'll go out there in the absolute darkness, absolute coldest part.
In the middle of a blizzard.
In the middle of a blizzard and test it.
That's probably the most intense job at Zipline. So props to the team in Wyoming.
That's
pushing
so cool.
the limits of the system.
Yeah, I think I read about it on our blog. That was really cool. What else should we know about simulated delivery? So all of this is happening in parallel. Any guesses around how many simulations or like miles of simulations that we've run? Is it tens, thousands, millions, billions?
As a company, we've easily ran 1 billion miles in simulation.
That's wild.
We used to keep track of it, and the number was just getting so astronomically high that we just stopped even tracking. It was hard to even understand what those numbers meant. But yeah, we've got, all the vehicle sets in here are flying around the clock. But then we also have software-only simulations that are running in our cloud, where they're basically running, we're running tens of thousands of simulations an hour.
That's so cool. So we're doing real-world testing. We're doing simulated testing. All of this is being done by our team, vertically integrated, and it's all also being done with our partners. I saw some folks were out at one of our partner sites getting some real-world learnings about how the system will be used inside of their actual restaurants, their facilities. So all of this is being done cohesively to make sure that the system is really just incredibly reliable when it's launching.
Yeah, exactly. And ultimately all of these systems, and the reason we're so vertically integrated are because our core competitive advantage as a company and the way we build the very best product is our ability to move really fast. And so by having every single expert in the building, if anything's going wrong or we want to improve any part of the system, you can walk up to an engineer, tap them on the shoulder, make that part of the system better that day, and then we can rely on all this automation to show that that change to that part of the system doesn't have an adverse consequence somewhere else in the system.
So by the time anything is flying in the real world, we have already put it through so many paces. And that's part of, I know we're at over 93 million miles of commercial, real world, actual deliveries to real people. And we haven't had a major safety incident. That's really incredible.
Exactly.
Ryan, thank you so much. I think we're closing in on the end of our tour. I don't see any other questions from our viewers, but thank you so much. And thank you to everyone watching.
Yeah, thank you. Until next time.